Linda, for the great introduction and for organizing this symposium. Okay, yeah, I have no disclosures. And so my job today in my talk is to give you some background on the global signal and provide context for the remaining talks. So first of all, we're going to start off by looking at what is the global signal and why do we really care about it. So the global signal applies to both task-related and resting state fMRI, but really the main controversy has been resting state fMRI. So we're really going to just focus on the global signal and resting state fMRI for my talk. And as most of you know, resting state fMRI, is widely used, and the field has identified lots of different resting state networks. In particular, the default mode network is one that we're going to focus on first. And so this paper, I think, if you want to trace sort of where the global signal regression controversy came in the field, we could probably trace it to this paper by Fox and Rakel from 2005. And here, what we see here is the default mode network with the posterior cingulate cortex, and everything that's correlated with it sort of makes up the default mode network. And what Fox and Rakel talked about was that there seemed to be an anti-correlated network, sometimes called a task positive, involving things like attention. And if you look at the signals in the default mode network, they go up and down in some manner. And then in this anti-correlated network, the signals go in the opposite direction. And so this was sort of this very attractive picture of sort of the interior aspect of the brain, sort of what you're thinking inside in the default mode network, and then your response to the external world. So it's sort of this yin-yang of the brain, and very interesting picture of how to look at the brain. Then about 4 years later, Kevin Murphy from the NIH group sort of raised the question and noticed that, well, yes, you can get these anti-correlated networks if you apply global signal regression. But if you don't apply global signal regression, you really don't end up with this anti-correlated network. And so really how we view the brain, whether it's alternating between these two networks or not, comes down to whether you believe you should do global signal regression or not. So that was the state of the art in 2009. 15 years later, we're still talking about it, okay? So let me tell you why. So let's first of all, just to get everyone on the same page, talk about what is the global signal and how you'd compute it. So what I'm showing you here are images from a single slice for different time points. And at every time point, I simply average over space the values, and then I assign that value. So here, where most of the voxels have a negative value, that would be a very negative global signal. Here, where they have a lot of positive values, that'd be a very positive global signal. And notice here where there's equal numbers of positive and negative voxels, then you'd end up with a very low global signal. Okay? So that's all the global signal is. Over time, you're just measuring the average signal across the brain. And then another thing we'll use is the term global signal amplitude. It's just a measure of how large is the global signal. For today, we'll just use the standard deviation over time. There's other metrics you could use if you wanted to. Okay, and so what is global signal regression? So we compute the global signal as we just talked about. It's the average whole brain signal. And then we simply project this global signal out of every voxel's bold signal. And essentially, it's just this one line of code. So essentially, one line of, say, MATLAB code or Python code can totally change your results. Okay? So why do you do global signal regression? Well, these are some maps where the seed voxel is in the posterior cingulate cortex. These are 5 different subjects. This map looks reasonable. If you're to present these maps to your PhD advisor, they'd probably tell you to come back next week with better results. And so you go back to your office, you do global signal regression, and voila, next week you come back with very nice results. 6 months later, you publish the paper, and all is good, okay? So the main reason you do global signal regression or any sort of type of pre-processing is to get meaningful maps, something that you can say something about. So for example, and if you do that, it tends to help results. For example, in this paper, they showed that if you apply global signal regression, you can strengthen the association between your resting state functional connectivity and various measures of behavior. And similar results have been reported by other groups as well. Okay, so now that we know there's some controversy about the global signal, then why don't we just not do global signal regression, okay? And so here, this is a nice review paper talking about different methods, and global signal regression is one of them, and historically controversial. Obviously, you could apply ICA and other things, and obviously physiological noise correction or white matter and CSF regression. And also, there's this thing called COMP-core, which has sort of been used quite a lot in various pre-processing pipelines. And this is similar to taking out regressing voxels or using signals out of the white matter and CSF. And the whole idea behind methods like COMP-core or white matter CSF regression is you're saying, well, there really isn't really much neural activity in those areas, and so let me use those as the regressors. Instead of averaging across the whole brain, let me just average or do a PCA over these sort of non-neural areas. And so if you do that, if you do global signal regression, you do get these anti-correlations. And if you apply this version here, anatomical COMP-core, you also get anti-correlations. And so this was sort of the excitement that you could get anti-correlation still without global signal regression. And in fact, for example, in pipelines like fMRI prep, COMP-core is sort of one of the things that you can use. That's not the only processing, but I'll use it as an example of why we really can't, why everyone is actually doing some sort of global signal regression, whether you like it or not, okay? And I have sort of mixed feelings about this because it's our group, Yishar Bazadi, a grad student in our group many years ago, invented COMP-core for task-related fMRI. We never intended it to be used for resting state fMRI. And we had very strict guidelines on when you should use it and very strict guidelines on how much postulated volume thresholds you should use and to test it against the task and only take out what can be explained by those things. Now, the field has gone on to use it for resting state fMRI with very liberal voxel-wise thresholds, and obviously in resting state fMRI, as we've heard in many talks already, we don't really know what's going on. So it is sort of a tricky thing to use. And so in this review paper here that I wrote about 7 years ago, the concern, which I still have, is that most of us who are using COMP-core are doing some sort of global signal regression because we're incorporating some signal from gray matter in our white matter and CSF voxels. And so if you're doing that, just know that you're not out of the woods and you are probably doing some sort of global signal regression. Okay, so let's talk a little bit about what the global signal is, dive a little deeper, and the title of this talk is The Global Signal is Everywhere, but Not All at the Same Time. Okay, and what do I mean by that? Well, first of all, it is everywhere. So for example, this is some nice data from Hongzhen right there, showing that the global signal in blue is very similar to what you get, the signal you measure in the big draining veins. This is some paper from Yunji Tong and Blaise Frederick's group, where they're showing that here's the global signal, and if you just measure oxygenation in your fingertip or even in your toe, you get something very similar. So essentially, it really is quite global. This is some recent work which is not showing up well here for some reason, but just showing you that if you do motion regressors, so for example, this is using AFNI 3D Volreg, and if you look at the motion regressors and you sort of look at, for example, the information that's carried in them, you can sort of see here in blue is the global signal, and then red is the information in the motion regressors that's carrying the global signal information. And so even if you're using motion regressors to correct your data, there's still global signal going to be in there as well, or could be, okay? So let's take another look back at the global signal, this slide that we showed before. So one thing you'll notice is that, for example, where the global signal is large is where the signal is very homogeneous across space, as you'd expect. And then where the signal is small is where you sort of already see these anti-correlations, okay? And these look very much like the anti-correlations you see if you did a sort of a standard seed-based map. And this relates to the work from Xiaolu and Jeff Dunn, looking at coactivation patterns, where they found that if you just looked at the areas where the brain is showing different patterns, sort of high signals here in the posterior instinct cortex, and you average those frames, you essentially get the correlation map. And the idea is when you look at the mathematics of correlation, it tends to be determined typically by the largest time points in your time series, okay? So what you can do with the global signal is you could say, well, let me just, here's the global signal in blue, and let me just ignore where I know where the global signal is large is where it's very spatially homogeneous. So let me just censor out all those high points and just keep the remaining time points. And if you do that, this is what you get with resting state, sort of seed-based correlation, and this is what you get by just averaging the time points that don't have high global signal, okay? And so these anti-correlations sort of exist here without any sort of mathematical confound, and you can argue that what we're really seeing in resting state data is these anti-correlations are going on in the background. They're just sort of washed out a lot by these large global signal fluctuations, okay? Another picture that's emerging in the field is some nice work from both the Penn State group and also UCLA and Georgia Tech groups, where looking at sort of moving away from this sort of mass univariate way of looking at data to looking at waves of activity, similar to some of the themes that were talked about in yesterday's educational session. Here's some nice work from the Penn State group showing sort of waves of activity going from sensory to higher order levels and then back down in the opposite direction. And these are tied to sort of global signal, the big peaks in the global signal. And if you do a different type of analysis and look at what's called a complex PC and look for these waves of activity in the brain, the biggest component, that you find actually turns out to be this global signal, okay? So however you look at this data, the global signal just keeps popping up. Finally, let's now switch gears and talk about what drives the global signal. And one clue came from work we did where we were looking at some data pre and post as sort of a administration of a drug, and we found out that we could get these anti-correlations that look fairly similar to what you could with global signal regression without doing any global signal regression. And you'll be happy to know that that's what you get when you take your coffee, okay? And so this is with caffeine. We found is a way of really lowering the global signal. So this is post-dose, pre-dose, how large the global signal is. We had EEG measurements, and so for this one, we'll use a ratio of alpha versus delta theta as a vigilance measure. And what we found is that in some subjects, there's really no change in EEG due to the caffeine, and these subjects show very similar functional connectivity patterns. And in those subjects that showed a large change in their EEG, you could really see sort of anti-correlation showing up after the caffeine dose, showing that we've sort of reduced this global signal, and there's an EEG signature of the global signal. And so what we found is if you plotted the change in the global signal amplitude versus the change in vigilance, you get this very strong relationship, okay? Other work has shown, for example, if you look at 15 minutes of resting state data from the HCP and look at the global signal amplitude, no surprise, as people get more drowsy, the global signal goes up, which makes sense because in general, as arousal decreases, we expect global signal amplitude to increase. You see this even within the time course. This is showing the global signal and vigilance, sort of the global signal has been inverted just so you can sort of see the correlation. And you can sort of see in patterns of high vigilance, the time points that have high vigilance, you see these anti-correlations, and in low vigilance, you see less anti-correlations. And then if you, for example, from Xiaolu's group, if you look at where the global signal is high, that tends to be correlated with sort of these electrophysiological patterns of activity that seem to be related to sort of arousal changes. So what happens then if you do global signal regression, essentially you are downweighting all these points where there's high and low vigilance, and you're just keeping the points where there's really not too much variation in vigilance. And so that might be okay in terms of essentially maybe global signal is okay because you're attenuating the effects of vigilance in your resting state fMRI data, and maybe that's what you want. But the point is you should be aware that that's what you're doing. Okay. This is just showing that these top-down and bottom-up patterns do seem to be related to arousal. And let me just, since I'm running short on time, let me just talk about sort of an emerging line of work where the global signal obviously is one thing we can measure. We've looked at EEG, but we can also measure heart rate, respiratory volume, CSF flow now. And it turns out all these things are related. Okay, this is another paper, preprint, where they're looking at other activities, including pupil diameter, respiratory volume, and once again, global signal is related to all of these things. Okay. And so maybe that's not so surprising. I mean, the brain is doing a lot all the time. It's coordinating our entire body. It's coordinating a massive amount of activity. I find this is from a mouse study, but it's sort of interesting where this is the neural activity, and this is the activity they look at, as the mouse is just moving its face all around and predicting from the face movements what the electrical activity should be like. Okay? And one hypothesis might be if we could actually measure people in the scanner and see what they're doing, all the fidgeting and everything, that might give us another handle on the global signal. So I think we have this picture. We typically, in fMRI, we really think we can isolate the brain and measure the brain in isolation, but really what we're measuring is sort of everything that's happening. The brain is not only affected by physiology, but it's also controlling physiology. And so when we're measuring something as global as the global signal, we need to keep this in mind. And so my last slide is that, and hopefully to set up the remaining talks, is that I think we're still at the phase where there is an elephant in the room, right, the global signal, and there's something going on. And so far we've got different views of that, right? Some people think it's a rope, some people think it's a fan, some people think it's arousal, some people think it's nuisance. So we have lots of different pictures of the global signal right now. And so hopefully the remaining talks can sort of address that, and hopefully we can have a discussion at the end. Okay, great. So thanks, and I'll turn it over to the next speaker. Thank you. Oh, I guess one question, right?
Great. We have received 2 questions. I suggest you take one, and then we'll leave the rest for the general discussion. So the first question has to do, has the recent work on potentially meaningful white matter bold signal influenced your view on GS regression validity? Oh,
the white matter bold signal? Yeah, I mean, I think that's another potential confound in using things like ComCore or other regressors, is that you could, if there is any neural signal in the white matter, which is still somewhat difficult to see or controversial, then obviously that's another reason that even though your pipeline is telling you you're not doing global signal regression, you may be doing some sort of global signal regression. Okay.
Thank you so much. Yes.